Okay, I think we can get started. Let's give it maybe 15, 30 seconds so that I can. Okay, I think we can get started. 30 seconds. Okay, everything seems to be working now. All right, let's get started. Welcome everyone to our Safari live seminar series. This is the third in a row. And this time we're going to be talking about data movement bottlenecks and benchmark suite for evaluating them and a methodology for them. And hopefully we'll have a good discussion on that and processing in memory. And Geraldo Oliveira will be the speaker. He is a PhD student working with me in the Safari research group. And this is one of the works that he has led in the group. And he's in general working in the processing in memory area and benchmarking and workload characterization. Okay, feel free to ask questions at any time. We'll try to collect the questions and ask at appropriate times on YouTube as well. Geraldo, would you like to get started?
Yeah, sure. Thanks, Honor. So as Honor said, I'm Geraldo, a PhD student here at Safari. And today I'm going to talk about our work DAMOV, a new methodology and benchmark suite for evaluating data movement bottlenecks. So first, I'm going to start with the executive summary of this talk. The problem that we are dealing here in this paper or in this work is that even though we know that data movement is a major bottleneck in modern systems, we still don't know how can you identify different sources of data movement bottleneck, because we have different sources of data movement bottlenecks that can happen in application or in systems. And also we cannot know, because of those different types of data movement bottlenecks, in a methodological way, with a methodology which is the most suitable data movement mitigation technique that can mitigate these different types of data movement bottlenecks. For example, those data movement mitigation techniques can vary from compute-centric data movement techniques, as caching and prefetching, to more modern or more new memory-centric data movement mitigation techniques, as in data processing for a given data movement bottleneck, for example. Therefore, the goal of this work is twofold. First, we want to design this methodology that can identify the different sources of data movement bottlenecks in an application. And second, we want to compare the benefits that compute-centric and memory-centric data movement mitigation techniques can provide for these different types of data movement bottlenecks. And our approach in this work is to perform a large-scale application characterization to identify the key metrics that can reveal the different sources of data movement bottlenecks in a large set of applications. Based on that, we draw four main contributions in this work. First is a large experimental characterization of 77,000 functions across 245 different application domains. And second, from this experimental characterization, we drive a methodology that can characterize applications based on the key sources of data movement bottleneck, and also the relationship of this data movement bottlenecks with three different types of data movement mitigation techniques, including data processing. Using this methodology, we designed DAMOV, which is a benchmark suite with 144 functions targeting the study of data movement bottlenecks or data movement related issues. And we take DAMOV and we analyze, or we drive different case studies to highlight how DAMOV can be applicable to open research questions related to data movement and the data processing design. So DAMOV is open source, is already releasing our GitHub repository, both our methodology framework and also the workloads that the 144 application workloads that constitute the benchmark suite, and is open source and free to use. So here's the outline for this talk. So first, I'm going to briefly talk about data movement bottlenecks and why these data movement bottlenecks can happen and potential solutions for data movement bottlenecks in a system. Then I'm going to give an overview of our methodology, which consists of three main steps, which I'm going to explain in details. Those steps are application profiling, locality-based clustering, memory bottleneck analysis. And after that, I'm going to give a brief overview of the four case studies that we drive using our DAMOV benchmark suite. So first, we are going to start with data movement bottlenecks. So data movement bottlenecks has become a problem in the system and can become a problem in the system for three different reasons intuitively. First, because the application does not have enough data locality and thus does not make effective use of the cache hierarchy. Second, because the DRAM bandwidth is not enough for a particular application. Or third, because the application or system cannot tolerate the high average memory access time to access DRAM itself. High-performance systems today have evolved to include different techniques that can mitigate or alleviate the data movement bottlenecks or data movement overheads in a system. Those techniques range for example, deep cache hierarchies or hardware prefetchers. We refer to such techniques as compute-centric techniques. However, such techniques not only come with significant hardware costs for the system, but also they often fail to alleviate data movement bottlenecks for a large number of applications. One promising solution that tries to alleviate data movement bottlenecks or in comparison to compute-centric architectures are the so-called memory-centric architectures. Memory-centric architectures alleviate data movement bottlenecks in a system by moving the compute resources nearby to the DRAM chip itself. One good example of a memory-centric architecture is the near data processing or NDP. NDP architecture or NDP core, which is placed nearby a DRAM chip, has access to data with abundant DRAM bandwidth and also shorter average memory access time. Therefore, we conclude that the main goal of near data processing is to mitigate data movement bottleneck in a system. However, data movement is not a new idea. In fact, the idea of near data processing has been around for at least 5 decades by now. However, only recently the industry has started to pick up on the data processing architectures, and over here highlight 2 of them. For example, the UpMem architecture released by a company of the same name in 2019 provides their NDP architecture that interconnects nearby DRAM banks, compute capabilities targeting to accelerate general purpose computing applications. This architecture can achieve a peak throughput of 0.9 tera operations per second. Another more recent example is the Samsung Film DRAM architecture that also integrates nearby DRAM banks, some computation targeting to accelerate neural networks. This architecture can provide a peak system throughput of 1.2 teraflops per second. Many recent works explore how to use the data processing architectures for other types of applications. For example, for graph processing, for mobile consumer workloads, for neural networks, DNA sequence mapping, databases, time series analysis, and many more. All of these works, they rely on different methodologies to identify applications that suffer from data movement bottlenecks, and often they use these methodologies as an indication that this application might benefit from the data processing. However, as I will show next, those approaches to identifying data movement bottleneck this correlation, this intuitive correlation with data movement bottlenecks and the benefits that it might take from the data processing architectures are not comprehensive enough, mostly because those applications or systems or those methodologies does not take into account they were not designed to take into account a large number of data movement bottlenecks. They were not designed at first to be correlated to the characterization of a data movement bottleneck to be correlated with NDP offloading or NDP suitability. And often they only use few metrics to identify a particular source of data movement bottleneck, which leads to problems like not identifying other potential sources of data movement bottleneck, which this single metric cannot identify by itself. Over here in this talk, I'm going to highlight 2 different types of data movement identification methodology that are commonly used in the literature. The first one is the roofline model, which correlates arithmetic intensity with the performance of application. And the second one is using the less level cache misses per kilo instructions, or MPKI, as an indication of memory bottleneck and thus NDP suitability. So let's get started by looking at the roofline model. As I said, the roofline model is a simple model that identifies memory bottlenecks in a system by classifying applications into 2 groups, applications that are compute-bound and applications that are memory-bound. The model it works as follows. It has 2 lines. The first line is called the compute roof, defined as the peak system throughput of the particular system under evaluation. And the methodology says that compute-bound applications below this roof are called compute-bound, and then compute-bound applications are shown by prior works to not take benefits of NDP offloading. The second roof is called the memory roof, defined as the peak DRAM bandwidth of the system times the arithmetic intensity of applications, and applications below this roof are called memory-bound, and prior works have shown that memory-bound applications are suitable for NDP offloading. So we take this roofline model and we analyze more the 40 applications, which I'm going to explain later on in this talk, to see if this correlation between memory-bound and compute-bound applications defined by the roofline model is comprehensive enough when analyzing the NDP suitability of application. To do that, we run these applications in a whole system and in an NDP system, and then we compare their performance characteristics. And based on that, we define the applications in 4 different classes. We have applications that run faster on the CPU compared to running on NDP systems, applications that run faster on the NDP system compared to running on the CPU system, applications which performance on the CPU and NDP systems are quite similar, and applications which performance benefits from NDP or whole system depends on different system configurations, as for example, the core count in the system. So based on that, we make the following observations. First, we see, as expected, that there are some memory-bound applications that do benefit from NDP offloading, as expected. We also see that there are some compute-bound applications that does not benefit from NDP offloading. In other words, they run faster on the CPU. However, we see a group of applications that are memory-bound, but can run faster on the CPU, or its performance might depend on different system microarchitecture configurations of the system. This behavior also happens for compute-bound applications, which have similar performance on the CPU or NDP system, or its performance might depend. Therefore, we conclude that the roofline model cannot accurately account for the NDP suitability of memory-bound applications. Next, we are going to analyze another metric commonly used to indicate memory bottleneck in a system and also NDP suitability. This metric is basically understand if application has high less level cache MPKI, which often is by high here often is a value higher than 10. If application has an MPKI larger than 10, we say this application is memory intensive and benefits from NDP offloading, as shown in the literature. So we also repeat the same experiments by running more than 4 workloads, classifying those applications based on their performance on the CPU and NDP system, and then we draw the 4 conclusions. The first conclusion is that, as expected, applications with high MPKI run faster on the NDP. Also, applications with low MPKI run faster on the CPU as expected. However, we see there are some applications with low MPKI that can run faster on NDP, have similar performance on CPU or NDP, or have its performance depending on these different system configurations. Therefore, we conclude that the less level cache MPKI alone does not accurately account for NDP suitability of memory-bound functions. So based on all of this analysis, I just want to conclude that there is no methodology right now capable of comprehensively identifying different sources of data movement bottleneck that the application might suffer from, and also correlates the sources of data movement bottleneck with the most suitable data movement mitigation technique, as being the CPU system with a deep cache hierarchy and prefetchers, or the NDP system. Therefore, the goal of this work is to develop a methodology that can methodologically identify sources of data movement bottleneck and also comprehensively compare compute and memory-centric data movement mitigation techniques. To do that, we've designed a 3-step methodology, which I'm going to give an overview next. So we developed a workload characterization methodology to identify the data movement bottlenecks in a system and application, and also the suitability of different data movement mitigation techniques in alleviating such data movement bottlenecks. For doing that, we use 2 different profiling strategies to develop our methodology. First, we use architecture-independent profiling tools, which can characterize the memory behavior of the application independently on the underlying hardware. And also, we use architecture-dependent profiling tools, which can evaluate the impact of the system configuration on the memory behavior itself. Our methodology, as I said, has 3 main steps. First, it takes as input the target application and its source code and input datasets. And then in step 1, we take this application and we profile the application using hardware profiling tools to identify functions within this application that are memory bound. Then we instrument the application using to demarcate the memory bound region inside the application, and then we apply the next steps using our new DAMOV simulator. Those steps are the following. In step 2, you do a locality-based clustering by taking the memory trace of the application and identifying architecture independent characteristics of this application. And then in step 3, we are going to collect the architecture dependent metrics and provide and execute a memory bottleneck classification based on those key architecture dependent metrics. Based on those two steps, step 2 and step 3, we classify the applications in different classes of data movement bottlenecks, which is the outcome of our methodology. So let's first get started by looking at step 1 of our methodology. The goal of the first step of our methodology is to identify functions within an application that suffer from data movement bottlenecks. To profile the application identifying functions that suffer from memory bottlenecks, as I said, we use a hardware profiling tool. In this work in particular, we use the Intel VTune profiling tool to identify such memory-bound applications. This profiling tool provides a metric called memory bound, defined as the percentage of CPU pipeline slots that are not utilized because of memory stalls. And we use this metric as an initial first level identification of the memory bottleneck within an application or function. Then we take this memory bound function and then we apply step 2 and step 3 of a methodology. I'm going to quickly explain step 2. So the goal of this step 2 is to analyze the application memory characteristics of the application's memory characteristics independently of the underlying hardware itself by looking at architecture independent metrics. We are going to look at 2 architecture independent metrics over here. The first one being spatial locality. And we calculate spatial locality by first collecting the memory trace of the application. And then based on this memory trace, we develop a stride profile histogram where in this stride profile histogram, each bin is going to store the stride, the number of times that particular stride appears, and in the y-axis is the count or the frequency of the strides across the memory trace itself. So here in this example, the application, the first access, the stride between the first access address 0 in this example and the next access address 1 is equal to 1. And then we take this stride 1 and increment the stride profile histogram in bin 1 to indicate that this stride profile has been observed. We take then in the end of the memory trace, we take this stride profile histogram and we calculate the cumulative distribution of stride profiles, and which is going to represent the final spatial locality value of the application. A spatial locality value close to 0 is caused by large strides or because of random access pattern in an application, or a stride locality close to 1 or a high spatial locality is caused by sequential access pattern within an application. The second architecture independent metric that we analyze is temporal locality. To calculate the temporal locality, we follow a similar methodology. We take the memory trace of the application, and based on this memory trace, now we are going to use a reuse profiler histogram, where each bin is going to represent how many times a reuse or how many times a memory address, a particular memory address is being repeated. And in this example over here, we have that address A repeats 4 times. So it's being reused 4 times. And based on that, we increment bin 4 in the stride profile histogram by 1 to indicate that this particular reuse has been counted in the memory trace. Similar to the spatial locality metric, we take the cumulative distribution of the reuse profiles from the reuse profile histogram, and this is going to define the final temporal locality value. So application with low temporal locality is caused because the application does not have enough data reuse within its memory accesses. And application with high temporal locality are those applications that have high data reuse within the application trace. Then this leads us to step 3, which is called memory bottleneck classification. And while in step 2, we want to understand the inherent application characteristics of related that can cause a data movement bottleneck by looking at architecture independent metrics, we also need to understand how this application interacts with the underlying hardware or the hardware features in the system. So to do that, we are going to use 4 architecture dependent metrics for the memory bottleneck classification to complement our methodology. Those metrics are the following. First, we are going to compute the arithmetic intensity of our application, or AI, which is defined as the number of float point or arithmetic operations per one cache line access. And we use this metric as an indication of the computational intensity of the application in terms of its memory requests. The second metric that we are going to use is the less level cache misses per kilo instruction, or MPKI, which is defined as the less level cache misses per 1,000 instructions. We are going to, as prior work shows, we are going to use this metric as an indication of the memory intensity of a particular application. Third, we define a new metric that is called last to first miss ratio, or LFMR, which is defined as the number of less level cache misses per L1 cache misses in the application. This new metric, as I'm going to show later, shows if the application benefits from the cache hierarchy, specifically between the L2 and L3 caches. And this new metric is a quite good indication of NDP suitability in a system, as I'm going to show later on in this talk. So the goal of, after we collect this metric, you also perform a scalability analysis from a particular application in order to identify the different sources of data movement bottleneck in the application itself. To do that, we are going to perform some performance evaluation and energy evaluation of each application using our new developed DAMOV sim simulator. This DAMOV sim simulator is an integration of the Z-sim simulator, CPU simulator, and the Ramulator memory simulator in order to provide a fast, scalable, accurate simulation of both a compute-centric system and also of a memory-centric system, in this case, a near data processing system. We take the simulator and we are going to execute 3 different system configurations or 3 different performance evaluations for each application using 3 different system configurations. The first configuration is of a whole CPU system, which is a standard compute-centric CPU system, which has a deep cache hierarchy with private L1 caches, private L2 caches, and a shared L3 caches. The second configuration is of an NDP system, which only have a single level of cache hierarchy, in this case, private L1 cache. And this CPU and this NDP system is interconnected to DRAM, interconnects to DRAM internally, so it does not go through the off-chip link of the system itself. In our paper, we evaluate a third configuration, which is a configuration that builds on top of configuration 1, and where we add a stream prefetcher in order to evaluate the third compute-centric data movement mitigation technique. Based on these configurations, we perform, as I said, the scalability analysis, where we vary the number of cores in the system from 1 to 256 in both host and NDP CPU cores. And we use different core organizations, those being out of order cores or in other cores, in order to drive our scalability analysis. We use such large number of cores in our scalability analysis. We go until 250 cores in the system because these large number of cores are required to explore the maximum DRAM bandwidth available in modern 2D stack memory devices, as shown by private works, and also because both host CPU systems and also NDP CPU systems can have varying number of cores. So this is why we go through this large number of core counts. And we use in all of the configurations that evaluate as the main memory, a 3D stack memory device that resembles the HMC or hybrid memory cube organization. In this way, the CPU system are going to interconnect to this 3D stack memory through fast off-chip serial links, while the NDP system itself is going to be sitting in the logic layer of the 3D stack memory device, and is going to interconnect internally to the DRAM device itself.
Geraldo, before you move on, maybe I'll ask a question if you go to the previous slide.
Sure.
Okay, this one. Okay, to clarify, you're going to execute applications and functions in both of the configurations, right?
Yes.
So in the first configuration, it's a traditional compute-centric system like today.
Yes.
And the second configuration is you're going to execute the entire function, entire application near memory, in these
Exactly.
near memory cores with a small L1 caches.
Yes, exactly. So it's good to highlight over here that in both configurations, we are using when you're doing the comparison, we are going to use the exactly same number of cores in both configurations, configuration 1 and 2, and also the same core organization. So if you're comparing if you're executing out of all the cores or using out of all the cores, in the whole CPU system, we are also going to use out of all the cores in the NDP system. In this way, we can see exactly the difference that those two systems are going to provide in terms of alleviate particular data movement bottlenecks, instead of seeing different core, some different core benefits that one architecture might provide on top of the other, microarchitecture benefits that one architecture provides on top of the other.
Okay,
So,
that makes sense. Yeah, you're keeping the core configurations constant between the two configuration. Okay, that's good. But you're changing the hierarchy
of the memory hierarchy.
So why don't you have a deep memory hierarchy in the NDP system? It may be good to discuss that briefly here.
Yes. So in the NDP systems, or the way that we are dealing with NDP systems here, it's hard to integrate a lot of compute capabilities or SRAM, CMOS per se, inside the logic layer of 3D stack system. So the area and power budget inside the 3D stack memory is quite limited. This is why we have to limit our CPU or cache hierarchy inside the CPU system to have a single level of caches. Usually, prior work calls this a shallow cache hierarchy, and we saw in this work that we need at least one cache in our NDP system configuration in order to capture some spatial locality of the application. Another good point here to highlight is that I talked previously about the UpMem system configuration, and even though this system is not the NDP system that we're evaluating here, is not exactly that configuration, because the UpMem system using different DRAM technologies, but the system configuration over there is quite similar in the sense that we have some cores connected to some local SRAM memory, and then we also have a fast DRAM memory bandwidth that the CPU cores can access to. So I would say that this is somehow becoming a common NDP system organization.
Okay, yeah, very good. I agree. And certainly the UpMem system has a processor and a scratchpad, L1-like scratchpad, and then the DRAM bank, which is very similar to your configuration, but you're of course evaluating a 3D stack memory here, which is a bit different, but in spirit they're similar. I agree.
Yes, exactly.
I have one more question, or maybe point, or maybe two more points. I think if people who are watching are interested, they can certainly watch our first live seminar on the UpMem system to really understand how the UpMem near data processing system is configured and designed and how it's evaluated. The second point I have is, so you have all this simulator and the benchmarks open source, and I think at the end you're going to give a tutorial about that, right?
Exactly. So by the end of this talk, I'm going to give a walkthrough or a tutorial about both our simulator and our benchmark suite. So stay tuned for that by the end of the talk.
Okay. Are there any other questions from anyone at this point? Since it's a good point. Yeah.
Yeah, I have a very quick question, Geraldo. Could you clarify how do you maintain coherence in both configurations?
Okay, this is a good question, and this is a good point in this in the way that we are doing this scalability analysis. So right here we are not doing. There are two types of configuration, right? Configurations across across the CPU cores in the CPU system itself or in the NDP system, and coherence across both whole CPU system and NDP system. For the first case where we need to keep coherency across within the same configuration, we use for the CPU system our standard MESI protocol that team itself implements. And for the NDP system, we use we only allowed the L1 cache to be a read-only cache, which simplifies the coherence protocol in the NDP system configuration. This is important because there is still there is no coherence protocol right now, or we still need to investigate which is the ideal coherence protocol for the NDP system, because as I said, there is some restrictions of the 3D stack organization itself, how we place the cores. We cannot have, for example, a shared directory, which the MESI protocol might use to do the coherence inside the CPU system. So this is why we decided to the one cache in the NDP system to be read-only. And then because of its read-only, we keep coherence by itself. Then there is the coherence across the whole CPU and the NDP systems. It's important to highlight here that we are not doing a concurrent execution of application or function. So the application does not run in the whole CPU system, then shifts to the NDP system, and then goes again to the whole CPU system. This is not the case over here. Over here, we take the function, and then we run this function on the whole CPU system, and then you take the same function and you run the same function in the NDP system itself. So because of that, we don't necessarily need to keep coherence across whole CPU because there's no concurrent execution happening. So,
okay, thank you, Geraldo.
Thanks, Juan. So I think I'm going to continue if there is no other question.
Okay, I think maybe I'll make a point on coherence also. I mean, this is certainly an important problem, how to handle coherence in a both between cores inside memory, let's say, like what you have over here, and also between CPUs outside memory and inside memory, right?
Yeah.
And I think those are both interesting problems for future work.
Yeah.
But yeah, it's not covered in this work for sure. And you eliminate those problems basically by making sure that L1s are read-only in the near data processing system, and you offload the entire function and the entire application so that there's no need for communication between the compute-centric cores and the data-centric cores, let's say.
Yes. Later on in this talk, I'm going to briefly talk about some problems related to NDP system design when I enter to the case studies. And over there, for those that are interested, there is a reference for on our book chapter, Modern Prime or Processing Memory Systems. And I would advise everyone that's interested on those problems that are on our talk about, as for example, coherence, to give it a look to that reference because it's quite comprehensive in that sense.
Okay, we have one more question on YouTube, and I think it's certainly a valid question. The question asks, can you mention why there are some applications that can run faster on CPU while being almost memory bound? I think this refers to your, if you go to the earlier picture.
Yes.
Maybe you can briefly mention that. It'll become clear, I think, when you do the characterization of the workloads, but I think it's good to briefly mention that.
Yes, so I think I'm a little bit, let me find that slide. So
yes.
Probably you are referencing this problem, this figure over here, the next one. This one. Oops. Sorry, this one. The problem over here is not necessarily that this application is memory bound and does not benefit from MDP. The problem is that we are using a single metric to classify this memory boundness. So the roofline model are pretty much classifying if the application is DRAM bandwidth bound. And this is one particular source of data movement bottleneck in a system. And then the problem is that this classification of memory bound by the roofline model is limited by the scope of memory DRAM bandwidth bound applications. As I'm going to show later on in this talk, this scope needs to be broader in order to identify other sources of data movement bottleneck, and thus our definition of memory boundness. And then we are going to understand if application can benefit from NDP or not, because of NDP might be solving a data movement bottleneck problem or not in that case. So it's because, in summary, it's because the definition of the roofline model of memory boundness or compute boundness is limited by the scope of DRAM, the application being DRAM bandwidth bound or compute bound, which is the right part of the roofline model.
Yeah, basically, I think what you're saying is this is not distinguishing enough between the applications that could benefit from near data processing. It's just looking at compute bandwidth, whether compute bandwidth or the memory bandwidth being the bottleneck in the throughput, but there needs to be more refinement in terms of understanding whether you would actually benefit from near data processing.
Exactly.
Okay, I think this will become more clear during your talk.
Okay, thanks, Honor.
Okay, I think we can continue.
Let me find this slide that I was before. Okay, it's this one. Don't spoil the talk over here. Oh. My PowerPoint keeps moving. Okay, so after doing this overview of the methodology itself, I'm going to start applying this methodology over a large set of applications. It starts with step 1, which is the application profiling. So in this work over here, we analyze 345 applications from different domains. Those domains vary from data mining, linear algebra, database, graph processing, genomics, machine learning, data analytics, deep neural network, graph processing, and many more. And over here, we are going to take these 345 applications, and we are going to identify those functions that are memory bound. And the selection criteria that we are going to use over here to identify if a function is interesting to moving forward to step 2 and step 3, if it's going to be if the clock cycle of that this function is going to take, or is going to be 3% of the total execution of the application, and the memory bound metric provided by your hardware profiling tool, which is Intel VTune, is larger than 30%. Why this metric? Why this filtering is like this? Because when we were starting developing this methodology, we did some initial evaluations of different values of memory bound and clock cycles from our application, and comparing it to the memory-centric and compute-centric or whole-centric NDP systems. And we saw that application that has a memory bound value less than 30% was not benefiting from NDP itself at all. And the clock cycle less than 3%, we think that is a reasonable percentage of the execution, because even though it might be slow in execution time, it can be significant in terms of energy consumption that application might have because of data movement. And another point that is quite important to highlight is that step 1 of our methodology is important as long as you don't know, let's say that if for application, you don't know application, or you are interested to know a new application and you want to understand, you don't know which function might be good for or interesting to analyze or not. This is why we are going to use this step 1 of our methodology. If you already have an application that you already know the function that you are interested on in evaluating, you can go directly to step 2 and step 3 because you already selected your function of interest, right? But we see that those two indications are good filtering in step 1 to move applications to step 2 and 3. And based on this selection criteria and this 345 application, after doing this 300 for the bottleneck classification, the memory bound analysis using Intel VTune of these 345 different applications, we find 144 different functions from a total of 77K or 77,000 functions. And we are going to select, we're going to subset these applications even further, or these functions even further, into 44 functions, which are going to drive our methodology in step 2 and step 3. And we are going to apply step 2 and step 3 over those 44 functions. And also, and later on, we are going to take the remaining 100 functions from this set of 144, and we are going to perform a validation of our methodology classification that I'm going to show later. So this is the output of step 1. And then we move to step 2, which is locality-based clustering. So we collect these, we take these 44 different functions that we subset from the 144, and then we collect the spatial and temporal locality values over there using the methodology that I explain later. And then we perform a locality-based clustering of those 44 applications using the K-means clustering algorithm. Based on that, we create, we see that using the K-means algorithm, we see 2 different clusters of applications. Applications being orange over here are those applications that have low locality, and over here in blue, we have applications that have high locality. And we see that the closer the application is from the bottom left corner of this plot, in other words, the lower the temporal and spatial locality that application has, the less likely it is going to take advantage, or it's less likely it's going to take advantage of a deep cache hierarchy, which is present on the whole CPU system configuration. Then after that, we apply move to step 3, which is the memory bottleneck analysis. So with those 2 classes of functions that I showed earlier in the locality-based clustering in mind, we are going to use the 3 different metrics for the memory bottleneck classification. Those being the LFMR metric, the less level cache PKI metric, and the arithmetic intensity metric, and also the temporal locality metric that we extract from step 2 to classifying the applications in different classes of data movement bottlenecks. And based on that, we found 6 different classes of data movement bottleneck that are merged based on those metrics and in this classification. Those classes of memory bottlenecks are first applications that are bottlenecked by DRAM bandwidth. Then we have applications that are bottlenecked by DRAM latency, applications that are bottlenecked by L1 and L2 cache capacity, applications that are bottlenecked by L3 cache contention, applications that are bottlenecked by L1 cache capacity, and applications that are bottlenecked by or are not necessarily bottlenecked. Those applications are basically compute bound. Important points to make over here. When I say application is bottleneck, I'm saying application is bottleneck in the perspective of the whole CPU system. So when I run this application in a regular whole CPU system, for example, application might be bottlenecked by L3 cache contention, for example. And then after doing this clustering, we are going to see the functions in each cluster that are going to benefit from the different types of data movement mitigation techniques in terms of performance and energy using our scalability analysis, which I'm going to highlight next. So I'm going to start doing the scalability analysis using the DRAM bandwidth bound applications. So applications that are DRAM bandwidth bound or applications in this class of data movement bottlenecks have low temporal locality, high LFMR value, high less level caching PKI, and low arithmetic intensity. We make the following observations. First, since the application in this class have high less level caching PKI, we expect these applications to exert high memory pressure over the memory subsystem. We likely are going to require significant high memory usage from the memory, the DRAM device itself. So to understand how this high memory pressure impacts the performance of the system, we observe how the performance scales when increasing the number of cores in the system. We make the following observations. Over here in this chat, I have one application from this class, and then in the x-axis we have the number of cores that we are executing our scalability analysis on, and then in the y-axis I have the normalized performance of the application. The applications are normalized to the execution of a single core execution. And in the secondary axis, I have the DRAM bandwidth consumption or the DRAM throughput that this application is leveraging. So as you can see from the plot, the performance of the application scales well as long as until the DRAM bandwidth saturates. And because since this application is accessed DRAM through off-chip link, at some point the maximum bandwidth provided by this off-chip link saturates, and then the application in this class tends to, the performance of the application in this class tends to saturate alongside the DRAM, provided DRAM bandwidth. And then we do the same experience for NDP system, for the same application using the NDP system itself. And then we see that when we increase the number of cores, the performance of the application does not saturate. In fact, it scales quite well alongside the attained DRAM bandwidth provided by the DRAM subsystem itself. Therefore, we conclude that applications in this class are bottlenecked by DRAM bandwidth, and basically the performance of the NDP system is better than the performance of the whole CPU system because of the higher internal DRAM bandwidth available inside the logic layer of that this NDP system is placed on. Likewise, we also analyze the energy for DRAM bandwidth bound applications when executing the application both in the whole CPU system and in the NDP system. So as I mentioned just before, applications in this class have high LFMR values, which tells me that the application does not benefit from L2 and L3 caches. So basically every L1 miss is going to, or not answer every, but most of L1 misses are going to also be misses in both L2 and L3 caches itself, and then go directly to the RAM. So over here in this plot, we show the breakdown of the energy consumption of both the whole CPU system and in the NDP system through different properties or different components of the memory subsystem itself, L1 cache, L2 cache, L3 cache, the off-chip link, and the DRAM chip itself for both host and NDP system configurations. And then I make the following observations. First, the host energy consumption for DRAM bandwidth bound applications is dominated by cache lookups, especially lookups at the L3 caches, and also by the power hungry off-chip data transfer. So if you see here, the red, the off-chip link and the DRAM bandwidth consumption is quite high for application in this class. On the other hand, when you look at the energy consumption of NDP system for the NDP cores, we see a large reduction in the energy consumption since the NDP system does not incur any energy consumption to access the L2 and L3 cache, because the NDP system does not have only have a single level cache hierarchy, which is the L1 cache. And also, since the NDP system is placed in the 3D stack memory itself, we can skip the power hungry off-chip links energy related to access the off-chip link. So based on that, we conclude that DRAM bandwidth bound applications highly benefit from NDP architectures when consider energy consumption, since the NDP system does not access L2 and L3 caches and off-chip links, leading to large system energy reductions. Then I'm going to perform the scalability analysis to DRAM latency bound applications. Applications that are DRAM latency bound have low temporal locality, high LFMR value, low MPKI, and low arithmetic intensity. So as I just said in the previous slide, since these applications that have high LFMR values does not benefit from the deep cache hierarchy. And we see how this is going to impact the host and NDP performance. So over here, I have the same plot as I showed before for the normalized performance when you increase the number of core for the host CPU systems. And we see that even though the scaling of the NDP system is quite good, the NDP system always outperform the host system for all of the core counts that you execute this particular application. To understand why this is happening, we rely on the average memory access time that these applications are going to take in both host and the CPU systems. And then you see that the memory access takes longer in the host CPU system than in the NDP system, due to the additional latency of looking up the L2 and L3 caches for requests that are going to miss in those caches themselves. And the NDP system can reduce such cache lookups, can reduce the average memory access time, since it can avoid such cache lookups. And on top of all of that, we still have the fact that the NDP system are going to skip going through the off-chip link for the requests that are missing the L3, thus further reducing the average memory access time for those applications. So we conclude over here that we have in class 2B applications that are DRAM latency bound, and those applications are not memory intensive because they have low MPKI, but they are latency sensitive instead. And the host performance is hurt by the cache hierarchies because of this these useless cache lookups, and also by the off-chip links, which is all adding to the average memory access time of these DRAM latency bound applications. Then we have L1 and L2 cache capacity applications. Applications in this class have low temporal locality. The last first miss ratio, LFMR metric, we observe that it decreases when we increase the core count in the system. I'm going to explain why next. These applications also are not memory intensive. They have low MPKI and they have lower arithmetic intensity. So since the applications since we observe that these applications have a decreasing LFMR metric, this means that when you are increasing the core count, the cache hierarchy or the L2 and L3 caches go from being ineffective to being effective. And we see how this impacts the performance again for both host and NDP system configurations. We make the following observations. First, at low core count, the NDP system performance scales better than the host performance, because these applications at low core counts are basically DRAM latency bound applications, similar to applications in class 1B, and also because these applications at low core count, as I said, had high LFMR values. However, when you start increasing the core count, over here in 64 is 250 and 256 cores, the whole systems start scaling better or providing better, more performance benefits than the NDP system for the same application. Again, we rely on the to break down the average memory access time to understand why this is happening. So basically, we conclude that when we increase in the core count in the system, the aggregate size of the L2 and L2 and L1 and L2 caches, which are private caches, also increases. It's important to say over here that in these experiments, we are keeping the L3 cache size constant, so it's always a fixed value, which is by note is 8 megabytes share L3 cache. However, the size of the L1 and L2 cache is not constant. It increases since those caches are private. It increases with increasing the core count. And based on that, by increasing the available cache size in the system, the application data starts to fit on the cache hierarchy on the whole CPU system, and DRAM access becomes less and less frequent. And then this is basically why this application starts to benefit from the whole CPU system at high core counts. Basically because now I have more private L1 and L2 cache, which can hold my data set or the memory footprint for the application itself. Then we conclude that the primary source of data movement bottleneck in class 1C is the limit L1 and L2 cache capacity that these applications have when executing low core counts. Therefore, while the NDP system improves the performance at low core counts, it cannot provide performance benefits across all core counts for these applications. Then we are going to analyze applications that are L3 cache content that suffer from L3 cache contention. Applications in this class have a similar behavior or opposite behavior from applications in class 1C that I just explained. These applications have high temporal locality. They have increasing LFMR value when you are increasing the number of core counts. They have lower MPKI, which indicates that they have lower, they are low in memory intensity, and they have lower arithmetic intensity also, or AI. So the increasing less first ratio or LFMR metric over here tells me the opposite from class 1C functions. Now the cache hierarchy was good or was providing benefits for applications when executing the whole system at low core counts, but I start increasing my core count, and the L2 and L3 caches becomes more and more inefficient for this particular application. And we see how this inefficiency impacts performance. So over here again, I have an application in this class, and then I have the wholesale NTP performance for this application, and I make the following observations. First, at low core count until 64 core counts over here, the whole CPU system scales better than the NDP system. However, when I reach 256 cores, the NDP system starts to outperform the whole CPU systems. We see why this is happening. And we understand that this is because the applications in this class are bottlenecked by cache contention. So at high core counts, this contention or the L3 cache contention reduces the cache effectiveness and causes the LFMR values to increase to near to 1, thus increasing the number of memory requests that needs to go to DRAM. So over here, I have the memory request breakdown, and you can see that when I start to increasing the number of core counts, the number of DRAM requests starts to increasing, mostly because of contention in the shared cache itself, because of the high parallelism that the application starts or the system starts to have. So we conclude that applications in this class are bottlenecked by the L3 cache contention, and at high core counts, those high locality applications basically become DRAM lattice bound applications. Then I have
Geraldo, I
yes,
think I'll stop you. There are a couple of questions that I will. It's good to handle at this point.
Okay, great.
So there's one question: is LFMR per core at last level or all cores? LLC. Okay, go ahead. Maybe you should answer that first, and then maybe I'll continue.
Okay, is for all of the cores. So it's the sum of L3 misses divided by the sum of L1 misses, the total.
Okay. Okay, that's a good question. It's good to clarify the exact metric. And I think the continuing part of the question is LLC could have cooperative prefetching effect. Wondering how that is factored in. I think this is related to the LFMR metric again.
Yes. So yes, so it can happen, right? One thread can fetch data to another, for example. I'm not going to talk about this particularly in this talk, but in the paper itself, we have a section where we see this clearly. We see that class 2A actually can be broken down into two different classes: applications that are suffering from coherence traffic in the L3 and the L3 cache. So this is pretty much one thread reading and another thread writing through the cache, and this being ping-ponged to the L3 cache itself, and then this creates L3 cache contention. And we have the applications which all that basically one thread is evicting the data from another thread. And we have a sensitive analysis in the paper where we use a different model for the L3 cache. Instead of having a fixed L3 cache size, we use a non-uniform cache access type of cache, where we increase the last level cache with the core count. And then you can clearly see this effect, because then in a particular application where one thread starts prefetching data to the other, and I have enough Dram L3 cache space to maintain this prefetching effect, this application is going to benefit more from the whole system instead of the NTP system. So this is highlighted in the paper, and I invite you to give it a look for more details on that.
Okay, and the paper is all online, yeah?
Yes.
Okay, thank you. That was Mark Charney asking the questions, and he also says, like the taxonomy. Thank you. There's one more question going back to the coherence issue. I think this is related to read-only L1 cache. There still needs to be some coherence, right? Even if it's read-only. And the question asks how coherence is ensured when a core reads data from its read-only L1 cache while another core has just written an invalue at the same data line in DRAM. I assume you have some invalidation mechanism, or?
Yes, yes. So we modify slightly the coherence mechanism in ZSIM. We pretty much we change how we include the bypassing mechanism that deals with this coherence across the different cores, and then we kind of rely on that in that modifications on the coherence mechanism itself. So even though it's a read only, and we try to not use a full MESI type of coherence protocol, we still have some evictions when this happen, when one thread writes and the other one is reading the private cache itself.
Okay, so it's a write-through cache with invalidation, right?
Yes.
Base protocol. Okay.
Yes.
Okay, this may be a good time to take other questions from the audience as well. Otherwise, we can move on. Anybody, any questions? Okay, I think let's continue then.
Okay.
Hi, I would like to ask a question, but
sure.
Okay, go ahead.
Yeah, so I'm not sure if this would be, I mean, feel free to correct me, but is there any concept of register pressure in NDP that we can derive from this? Like, can we predict if we have an NDP core, how would the register pressure in those cores would look like as compared to the traditional approach?
This is a really good question. So over here, since the registers itself are tied to the CPU organization itself in your system, and you're keeping both constant, we do not evaluate that in your methodology. I'm just trying to think if register pressure would fit in one of those classes of data movement bottleneck. I expected applications that are in the application that have high temporal locality might suffer from some register pressure, but I'm not sure. We need to evaluate that in the system. In this work over here, mostly focus on the other part of the memory hierarchy instead of in the core design itself. But this will be excellent to analyze pretty much how many registers are needed in the NDP core design. I don't have an answer right now for that one, but definitely it's interesting to check.
Sure, thank you.
Thank you.
Yeah, that's a good point. I think in this work the assumption has been you don't change the program and the core between NDP and, let's say, compute-centric systems of today.
Yes.
But yes, if you have the freedom to customize the cores for an NDP system, then you may need to rethink how you build the register file, L1 cache, and the memory hierarchy in general.
Yes, yes. And maybe other components of, for example, the load store keys, the number of entrants, all of those type of things also might be quite important to give it a look when designing a core microarchitecture for NDP system.
Yeah, exactly. This is something that relates to something that I wanted to ask you, Geraldo, is how could we use your methodology to, or at least for a start, to come up with a tailored design for a specific class of applications?
Yes. So I think our methodology is good for identifying, or is a good start first to filter applications that we are not interested on. For example, compute bound applications that I'm going to show later. And later on is good to, because over here we are just clustering the applications based on those metrics, right? But those metrics tells us more about the application other than the class of data movement bottleneck. For example, the temporally special locality is an excellent indication of, for example, if the application, if you are going to design a core for the NDP system that needs to access data in a sequence access pattern or in the random access pattern. And this changes, right? How you design the issue, the fetching and decoding and this part of the core or the accelerator, the number of load store queues or that you need to have to maintain a peak bandwidth of the NDP core, all of those type of things. So those metrics are a good indication of those. And in our paper for class 1A application, actually, we have a discussion about these applications that might benefit from different type of NDP accelerators because they are either doing sequential access pattern or they are doing random access pattern. And then we discussed how this accelerator might look like for this particular class of bottleneck using those metrics. Another metric that is really good to look when you design an NDP core design is the arithmetic intensity. Over here, we're just saying that application has high or low arithmetic intensity, but even though the applications might have lower arithmetic intensity, we can look at how low is this arithmetic intensity. So the application is doing really, really few operations. We don't need that many LUs in your system. But if this application is doing somehow medium to low, or if this low number is not as low as you might need to have some clever design of the LU or how you share the LU, because as I said, the NDP system is quite constrained regarding to area and power budget. So I think this is why the methodology would be useful for first to segment the applications that you might be interested in looking at as a specialized NDP core design. As second, it would be, because you already collected all of those metrics for doing the initial classification, would be interesting to look further in each metric and start to think which memory, what is this metric telling me regarding to the memory characteristics of the application itself.
Okay, and what about extending some of the metrics? For example, if you watch the presentation about the UPM architecture, one of the things that we explain is that the performance is very dependent on the type of arithmetic operations that you have to do as well, right? So maybe here, going deeper into the definition of arithmetic intensity would also be useful, right? When targeting specific architectures.
Yes, this is excellent actually, because right here we are only looking at, we are summing both float point operations and integer arithmetic operations to calculate arithmetic intensity. And then we lose this difference, right? But float point multiplication is way more costly than integer LU, right? In terms of area. And even though we do not look at this metric right now, in your that would be useful. That can be doable with our DAMOV sim simulation. Would be easier. So first, because our simulator, I'm going to talk about it more in details later. But it gives a breakdown, for example, of the different type of micro operations that the applications are executing in itself. You can see like the number of float point or integer operations, and based on that, you can compute the different, let's say, arithmetic intensity in terms of integers and arithmetic intensity in terms of float point operation, and then can be a clear indication of like, even though if this is memory bottleneck, can I fit the logic that I need in the logic layer of my or the substrate for my NDP system design. So. Yeah.
Okay, yeah, very good. Thank you. That's
Excellent.
can be very useful. Thank you, Geraldo.
So if there's no other question, I will continue.
Yeah, sounds good. Let's continue.
Excellent. So I stop over here, and now we have the L1 cache capacity bottleneck applications. So applications in this class have high temporal locality, low LFMR, low less level cache MPKI, and lower arithmetic intensity. So the low LFMR and low MPKI of this application and high temporal locality indicates the application in this class are actually making really effective use of the L2 and L3 caches. And on top of it, the applications have low memory intensity because of the low MPKI. Also, something that is important for application in this class that's going to contrast with the application in the next class is that application in this class have lower arithmetic intensity, which tells me that I'm executing fewer operations per byte access from the memory hierarchy. Then we again repeat the scalability analysis for application in this class, and we make the following observation. So even though the NDP system scales quite well for this particular application, we see that the host NDP system performance also scales particularly similarly to the performance of the host subsystem. Even though the important to highlight over here, the NDP system does not include as much SRAM area as the host subsystem includes. So the host system, the NDP system, as a reminder, does not have L2 and L3 caches. But even though by removing L2 and L3 caches, I still can, the NDP system can still perform similarly to the host CPU system for these applications. So when you look at the breakdown of the average memory access time of this particular application, we can clearly see why this is happening. This is happening because applications in this class are being dominated. The execution, the average memory access time for these applications are dominated by the access to the L1 cache. So applications in this class, they do really few access to, not necessarily really few, but they do few access to the L2 and L3 and DRAM caches, and most of the access are concentrated in the L1 cache itself. As expected, application in this class has high temporal locality. And because of that, I can eliminate the S2 and L2 and L3 caches in this memory subsystem, and still sustain similar, the same performance of the host CPU system in such a case. So we conclude that applications in this class, even though NDP does not mitigate any memory bottleneck for application in this class, it can be still quite useful to reduce the overall SRAM area and thus costs for applications that are in this particular category, L1 cache capacity bottleneck application. Then finally, we analyze compute-bound applications. And applications in this class have high temporal locality, low LFMR, low MPKI, and high arithmetic intensity. Similarly to applications in class 2B or L1 capacity bottleneck applications, applications in this class are going to make effective use of the L2 and L3 caches, and they are going to have low memory intensity. However, differently, they have from applications in class 1 2B, they have high arithmetic intensity, which means that I'm executing many operations per byte. When I look at the performance of this particular application, we see that the whole system always outperforms the NDP system, mostly because these applications in this class are highly making effective use of the L2 and L3 caches itself. So this is different from the other case where even though you are not accessing the access to the L2 and L3 caches were quite few, but they were not penalizing the performance. They were not basically in the critical path of the performance of the application, but over here they are. So it's quite important to maintain the L2 and L3 caches for applications in this particular class. So we conclude that class 2C functions do not experience large memory bottlenecks and are not a good fit for NDP systems in terms of performance. In our paper, we show that they might benefit from NDP systems in terms of energy. So to conclude, our scalability analysis leads us to 6 distinct classes of memory bottlenecks, and we invite you to check our paper for a more comprehensive discussion about the performance and energy scalability of each memory bottleneck class. So is there any question on there? Otherwise, I'm going to go to the validation.
I think let's continue.
Okay, good, thanks. So next, now we did this classification with 44 applications, right? But as a reminder, in the beginning, we had identified 144 functions. So now we want to see if this classification of 6 different classes of data movement bottlenecks can accurately accommodate the 100 extra applications that we found in step 1. So to this end, we are going to have, we want to evaluate the accuracy of our workload characterization on a large set of functions. And to do that, we are going to execute a two-phase validation of our methodology classification. So that's this validation in the first phase. We basically take the 44 application functions and the key metrics that we use to classify those application functions, and we calculate the threshold values that are going to define the low and, because I keep saying low, high, so I calculate the threshold values that define those low and high boundaries for all of those 6 different classes of data movement bottlenecks. Then we apply step 2, and step 3 of our memory bottleneck classification to the remaining bottleneck functions that we obtain in step 1, and we use these threshold values in step 2 that we define in phase 2 to classify the remaining 100 functions into one of the different classes of data movement bottlenecks using those threshold values calculated in phase 1. And we say that application has been accurately classified into one of those 6 different classes of data movement bottlenecks if and only if it is going to fit the definitions of the assigned class using the threshold values obtained in phase 1, and also follows the expected performance trends of the assigned classes when the application is executed in the host CPU system and in the NDP system itself. So following this methodology, we see that our classification has a high accuracy. We can classify 97% of the functions into one of the 6 different classes of data movement bottlenecks. And we expect that this accuracy can be further improved by incorporating more workloads into our workload suite, and also fine-tuning each metric in over an even larger set of applications or application functions. So we have way more analysis in our paper if you are interested. I think I highlight some of them over here. For example, the effect of less level cache on our classification. And over here, as I said, we use a non-uniform, we repeat the scalability analysis using a L3 cache size that increases with the core count in a non-uniform cache access type of organization. So the caches are interconnected using a to-do mesh networks. And we see that one of the key conclusions that we derive from this analysis is that pretty large L3 cache sizes, for example, 212 megabytes, which is the largest size that we evaluate, can mitigate some cache contention issues. And this is exactly what I was talking about, for example, class 2B functions that can be further split into 2 subsections, subclasses. And those are those applications that this prefetching effect happen, and then I don't evict data that another thread was working on. Then we have a summary of our workload characterization methodology, and in this summary we repeat the whole workload characterization using in other cores for the host and NDP systems, and we see similar trends across all of the 6 different classes of data movement bottlenecks. We describe the limitations of our methodology, and also we highlight using a dendrogram analysis the benchmark diversity of our benchmark suites. And for all of that, again, I invite you to check the full draft of our work. Finally, I'm going to briefly...
Can you, Geraldo, sorry, can you very briefly summarize what are the limitations?
So, okay, so the first limitation that we have is that we are doing the computation, the whole analysis is bounded by functions, right? So I keep talking about functions in an application, and this can be a limitation because we are not seeing the interactions from one function to another function. And this is particularly important when you are doing concurrent execution of a host CPU in an NDP system, where if I offload a function, a memory bound function, to an NDP system, I need to make sure that later on, I don't cause more data movement bottleneck from the output of the computation that offload to an NDP system to the whole CPU system itself, which can kill the whole performance and energy benefits that this offloading might have brought at the first place. So the first limitation is being limited by this function analysis. Another limitation is that we simplify a lot the design of the NDP system, right? So we use read-only L1 caches. We execute the same core configuration in the host and the CPU system, and we assume a L1 cache size of the same size of the L1 cache system. So this is another limitation because we are skipping some of the challenges that are required to design a NDP system, a real NDP system. As for example, coherence I think is a good point over here, or is a great example of one of those limitations or simplifications that we are doing. Another limitation is that we are not assuming any area constraint of the whole CPU system. And any area constraint in the point of view of the NDP system configuration itself. Why this is a problem? Because as I said, you cannot fit 256 out of 4 cores in a logic layer of a 3D stack memory device. So as an example, the HMC device itself, HMC generation 2, the logic layer itself has a area budget or a free area budget of 4.4 millimeters squares per volt, and you have 32 volts. This is enough for you to fit only 6 out of all the cores in that area. So this is also one limitation because we're not evaluating that those 6 cores compared to the 256 cores of the whole CPU system. Why is that? Because we are interested in characterizing data movement bottlenecks, not necessarily to do a design space exploration for NDP system designs. So this is why we don't consider this area or power budget overheads or limitations that the NDP system might have. So I think if I didn't forget any, I listed all of them. But I think at least I listed the most important ones.
Okay, thank you, Geraldo.
Thank you.
These limitations are described in the paper, right?
All of them are described in the paper, yes.
Okay. There's one more question, maybe somewhat tangentially related to this, but Mustafa Ali asks, could we go deeper in the NDP system and analyze application boundedness inside the NDP levels, core, L1, and DRAM, or is it not worth it? Or maybe is it not within the scope of this work?
It's not in the scope of this work, but I think I think this is related to a question that Adi asked before about designing the ideal NDP system configuration. So now I think the good thing about this work over here is that now we segmented the applications and now we know which application we should look at. And now you can look at these applications and you can repeat the same methodology inside the CPU and the NDP system. And then you can see if I have a general proposed NDP system, what is now my bottleneck? Is my bottleneck my register file, or is my bottleneck my my backend? Is my bottleneck my number of load store queues that cannot exploit cannot issue enough, cannot hold enough load and store instructions? I can repeat all of this methodology with a more microarchitecture driven mindset, and then design the most or the best NDP system configuration for a particular application or group of application. So definitely, I think it's a really good question.
Okay. Are there other questions from anyone? That's a good point. A good point to ask questions before Geraldo moves on to case studies of how to use this methodology and the simulator. Yeah, I guess we can continue, Geraldo.
Thanks, Honor. So now I'm going to talk about the case studies. So as we've just been discussing, I think throughout this talk, there is still many open questions related to how to design an NDP system. As I said early, I could not highlight more for those that are interested on learning more about NDP system design challenges to look at this reference 8 over here, which is a modern primer on processing memory It is available on Honor's main page. So I'm going to just briefly talk about some of those points that this work talks on more details. So those problems are, for example, how can I interconnect NDP systems in a 3D stack memory device? Or how can I do data mapping and data allocation for application in an NDP system? Or how should I design my NDP how should be the microarchitecture design of my system? It should be accelerator, should be a general purpose core, and how does it look like? How should be my offloading granularity when I offload something to paint? So far, I'm being offloading stuff to the NDP system in terms of functions, but I could offload a single instructions or a limited size of block of instructions or a whole application, or how I program the NDP system itself, how I maintain coherence across the NDP systems and across the NDP system and the host CPU system itself, how I integrate the NDP system over the whole traditional compute system or architecture, for example, and many, many more. So the goal here is to demonstrate how our benchmark suite, how DAMOV is useful to study some of those NDP system challenges, in special, I think the first four, all of those. So those case studies are those 4 ones that I'm showing over here. So the first one is about interconnection. The second one is about the design of an NDP accelerator. The third one is about the design of the organization of the NDP core in terms of in order of other cores, considering area and power budget for these cores. And the last one is about how should I offload some computation to NDP. So I'm going to briefly talk about all of them here. So in the first case study, we use DAMOV to evaluate the interconnection network overheads that INDP core that is placed in different vaults of the 3D stack memory suffer from. So as I said, we are assuming a 3D stack organization where each inside the stack is divided in different vaults, and which are vertical partitions. Each vault has its own memory controller, and then we place some computation in each one nearby to each one of those vaults connected to one of those memory controllers. And the NDP system needs to communicate with each other, right? So there is we need some interconnection of network over here. The interconnection network that we assume over here is a simple 2D mesh organization, is a 6x6 mesh. And I think if I'm not wrong, we assume that the overheads of going from one vault to not one vault, to go for one router to another in the mesh is 3 hops. So then we, based on that, we calculate the overheads that this interconnection movement or this interconnection network is causing on the performance of the NDP system compared to the host CPU system again. And then you see that portion of the memory request and NDP core issues goes to remote vault, and it's not a small portion. It's quite a large percentage. I cannot remember from the top of my head the number, but if I'm not mistaken, actually the local for some applications, the number of local requests is actually only around 25%. All of the other memory requests go to remote vaults. Again, don't quote me on this number, but it's something this order of magnitude. And then we see that what this is causing in the end is increasing the memory access latency for the NDP cores. We can actually penalize the performance that the NDP core can provide compared to the host CPU system itself. So we believe that DAMOV can be employed to study better data mapping and the interconnection network schemes to minimize the number of remote memory access that the NDP core might execute, and also to provide better interconnection networks that can provide lower interconnection overheads for the NDP system design itself. Then in the second case study, we want to evaluate the benefits that NDP accelerators can provide compared to a compute-centric version of the same accelerator. So based on that, we take applications from 3 classes of data movement bottlenecks: bandwidth-bound applications, latency-bound applications, and compute-bound applications. And then we want to see, is our observations that we saw from the host point of view or from the general proposed course point of view, are they going to be the same observations that we are going to see when you use accelerators? And then we see that the NDP accelerators is faster than the compute-centric version of the same accelerator for applications that are Dram bandwidth-bound and Dram latency-bound, and is lower for applications or does not provide benefits for applications that are compute-bound. And this key observation, then we conclude that the key observations that we do for each class of data movement bottleneck using general proposed core counts holds also for NDP architectures. Then in the third case study, we perform an ISO area and power performance evaluations to compare an NDP system using in order for the cores. So as I said here, if I have an NDP system and I want to architect the NDP system using out of all the cores, I can place 6 out of all the cores in the budget of the 3D stack memory device itself, power and area budget. And I can place, I don't remember the number by the top of my head, but around, I think one other magnitude more in other cores in the same area budget. So basically want to compare those two organizations and see what happens. So we see that even though the using in other cores in the system compared to using out of other cores provides better performance for all of the applications that we evaluate in this case study, because basically I have one order of magnitude more cores in the system, not the cores in order for the cores. The difference of performance for those applications are not equal. So there are applications that takes way more benefits of using the many core setup using the order for the cores, but some other applications, the difference between order for the cores is quite small compared to in other cores. And based on that, we conclude that using the in-order cores for such applications is limiting the performance of the whole potential performance that this in-order core system could provide for such applications. And this happens because since we are using other cores, the static structure and scheduling mechanism available in the in-order cores is not enough to exploit enough memory parallelism in order to extract benefits of the 3D stack memory device itself. So we believe that we can design better NDP systems by leveraging techniques that enable dynamic structuring and scheduling without incurring the large area and power overheads of having an out-of-order cores for an NDP system. And DAMOV can help in this analysis and develop of such NDP architectures. So finally, in the fourth case study, we want to evaluate the benefits of offloading a small portion of the code, for example, a basic block to NDP. Instead of offloading the whole function, I'm going to offload a single basic block, which actually simplifies a lot the design of the NDP system, assuming that the area that I need to fit a basic block is way smaller than the area that I need to fit a whole function or a whole application. So the first observation that we do, we take the 44 applications that we used earlier, and then we create a histogram of basic blocks, less level cache misses per basic blocks. And then you see that for many applications, few basic blocks represent most of the less level cache misses for that particular application. And then we take these few basic blocks and we offload them to an NDP system instead of offloading the whole function. And then you see that this offload is enough to provide performance benefits for some of those applications. And we see that we can provide up to 25% performance benefits by offloading some of those basic blocks. So we believe that DAMOV can be used to identify those simple NDP blocks or NDP primitives or instructions that can enable building efficient NDP systems in the future. So I'm going to briefly talk a little bit more about one of these case studies, which is the NDP accelerator. And for the other ones, I reference to the paper. So as I said earlier, the goal of this case study is to evaluate the difference of a compute-centric versus a memory-centric or NDP accelerator. So by compute-centric accelerator, what I mean is that I have some custom accelerator that is interconnected by some off-chip link to a 3D stack memory device. And then I have an NDP accelerator, which is placed in the logic layer of the 3D stack memory and does have access to the memory bandwidth through by having higher DRAM bandwidth and shorter or lower average memory access time for this particular custom accelerator. And it is important to highlight that the methodology that we use over here is a little bit different from the one that I've been providing so far. To customize these accelerators, we use a tool that is called Aladdin. It's referenced here, reference 9. And this tool allows you to generate a custom accelerator per application. Pretty much it takes the application, generates a LLVM IR basic trace and data flow graph of the accelerator. And then based on this data flow graph, it customizes the accelerator based on some restrictions that you pose to the system based on the number of LUs that you have or the number of load store units that you might have. And then we use this methodology to design these custom accelerators. And then based on that, we make the following observation. So over here, the y-axis, I have the speed up of the NDP accelerator over the compute-centric version of the same accelerator. And then I have applications from 3 different classes. I have applications from class 1A application. This application here is, as a reminder, DRAM bandwidth bound. I have applications that in class 1B, which are DRAM latency bound, and applications in class 2C, which are compute bound. So then again, we compare the speed up of each one of those accelerators, the NDP accelerator against the compute-centric version of the same accelerator, and make the following observations. First, as expected from more early classifications, DRAM bandwidth bound accelerators highly benefit from the NDP accelerator compared to the compute-centric version of the same accelerator. Why is that? Because the application is compute bound, as we classified earlier. So it is going to take advantage of the higher bandwidth inside the logic layer of the 3D stack memory device. Second, we see that the NDP accelerator provides more performance benefits compared to the compute-centric accelerator for the DRAM latency bound application for similar reasons. Since I'm inside the logic layer of the 3D stack memory device, I skip the off-chip link and then I reduce my average memory access time. Even though the speed up provided by the NDP system for class 1B is lower than for the application in class 1A. Why is that? Because often the reduction in DRAM or improvement in DRAM bandwidth in the 3D stack memory architecture when you enter the DRAM chip itself is larger than the actually reduction in the memory access time. This is why the speed up is larger from the DRAM bandwidth bound application. And finally, we don't see any benefit from compute bound application as expected, because this application is not suffer from any memory bottleneck. So the performance for both systems are quite similar. Therefore, we conclude that the performance of the NDP accelerators are in line with the characterization that we did earlier for the memory bound classes. And then we expect that our memory bound classification can be applied to study other type of system configurations, including NDP accelerators. Again, for more details of each case study, I reference to the paper. So finally, I just want to highlight that our DAMOV, both the benchmark suites and the toolchains are open source. And they are, this is a screenshot of our GitHub, the Safari CNU GitHub. And over there, we are going to be able to download the DAMOV benchmark suites and also the DAMOV simulator itself. And to get all of that, you can just clone our Git repo. So I'm going to quickly conclude this talk. So the problem that we are dealing throughout this whole talk is that DataMove, even though DataMove is a major bottleneck in our systems, we still could not identify in a comprehensive and systematically way different sources of data movement bottleneck in application and the most suitable data movement mitigation technique for a particular data movement bottleneck. Therefore, the goal of this work is twofold: to design this methodology that can identify the different sources of data movement bottlenecks, and also to compare the performance and energy of compute and memory-centric data movement mitigation techniques. The key approach that we took in this work was to perform a large-scale application characterization to identify the key metrics that can reveal the sources of data movement bottleneck for a large number of applications. And we draw 4 key contributions based on that. The first one is our experimental characterization of 77,000 functions across 104 applications from various domains. Second, a methodology that we use to characterize applications based on their data movement bottlenecks, and also the relation of these data movement bottlenecks with 3 different data movement mitigation techniques, including the data processing architectures. Third, we take this methodology and we apply it to these 345 applications. And based on that, we develop DAMOV, the benchmark suite for data movement related studies. And also, finally, the 4 case studies, which highlights DAMOV applicability to open research problems related to NDP system designs. So again, DAMOV is open source, is available in your GitHub. So thank you so much for listening so far. And we are going to have a tutorial later, but I'll be glad to take questions now.
Okay, thanks, Geraldo, for the detailed talk. Before you start the tutorial, maybe we should handle some questions. Are there any questions that people have? I think there's one question on YouTube while people are thinking of questions, perhaps. One question is, if you go to the accelerator study, shouldn't the compute-centric accelerator be faster than NDP for compute-bound apps? This is for the rightmost bars, I think, over here, right?
Yes. Yeah, exactly. So,
I think it continues as since computing in DRAM is generally slower due to process limitations.
Yes. So over here, this methodology is quite simplistic because we are not assuming different frequencies inside the DRAM and inside the custom accelerator itself. We assume that both of them operate in the same operating frequency, and also that we are not limiting neither accelerator in terms of the logic that it can have in the accelerator itself, or in terms of the area that it can take. Why do we do that? Because the goal over here is the same goal as we were having before. The goal is to highlight the data movement bottlenecks using a different system configuration, in this case, the accelerator itself. So this is why you mostly configure the system to exacerbate the differences in the memory hierarchies for those 2 systems that we are evaluating. Yes, I expect to, if we repeat this experiment and consider both the area limitations and the difference in frequency that a custom accelerator might have in the logic layer, and the same custom accelerator might have being in a SoC or something like that, I do expect that the last bar for the computing accelerator to be higher than the bar for the NDP accelerator. So definitely something that is possible.
Yeah, but over the course of time, the logic layer in 3D stacking can improve significantly as well. So even though the logic layers of recent years have not been, let's say, as good, as 3D integration and fabrication technology becomes better, I think logic layer in a let's say 3D stacked system is going to become much better, and it's going to approximate what we have today, in my opinion. And
yes,
yeah,
actually to the logic layer in the HMC system, even though the NDP system has HMC memory device have been discontinued, at the logic layer, memory controllers inside the logic layer over there were operating at 1.25 gigahertz per second. This in 2015 when the system was released. So it's quite a high speed already, right? So it's different, for example, from the Optimian system that needs to operate at a lower frequency because the DRAM and the computation was being fabricated using the same fabrication process, right? Over here, the integration is a little bit different. We don't necessarily fabricate them together, just integrate them through silicon vias. So this enables the logic layer to have a little bit higher frequency than fabricating both custom accelerator or NDP system and DRAM using the same fabrication process. Of course, this creates another problem, that is thermal dissipation, but this is, we can discuss this later.
Yeah, there are other works handling that. But yes, it's important to distinguish between computing in the logic layer in a 3D stacked system versus computing inside the DRAM layer, inside the DRAM chip. DRAM fabrication process is completely different.
Yes,
for sure. Okay, there's another question. Did you consider how the data is mapped in the DRAM while calculating the cost? I'm not sure what cost means over here, but maybe you can handle the data mapping.
Yes, we did not consider how data mapping was we basically didn't do any spatial data mapping for the NDP system. So whatever data mapping or whatever interleaving the 3D stack memory was using for the whole CPU system, we use for the NDP system for fairness, right? Because I can't place the data mapping, for example, to minimize the interconnection network or to maximize the bank throughput, for example, of a bank in the 3D system. But then I think this is not the goal of the overall goal of this talk so far, right? It was to identify data movements instead of provide the best performance for NDP system. But yeah, we didn't consider different data mappings or interleaving in this particular work. And pretty likely, if you do that on top of the speedups that you're already showing for the applications that we are analyzing, likely your performance or your cost or whatever metric is going to be, improve compared to the whole CPU system, right? So,
yeah. So I think to add to that, basically, you're not changing any of the mapping that you use in the compute-centric version in the near data processing version, right?
Yes.
Yeah, but you can certainly do better if you change the mapping and customize it for the near data processing system.
Exactly.
Because the mapping is probably customized for the compute-centric system today.
Yes, yes.
Yeah. Okay, that's good. There's one more question, follow-up, I think, on the logic layer. Isn't logic layer-based NDP exposed to less memory bandwidth than near bank NDP? I think now it's going back into the design of the near data processing engine, which is really not within the scope of this work. But the question is, do you think that might change your current insights?
I do not think that's going to change the current insights. Why is that? Because all of the conclusion that we are taking is in the point of view of the whole system. So when I say that application is DRAM bandwidth bound, this application is DRAM bandwidth bound on terms of the whole CPU system, or is DRAM bandwidth bound on the perspective of the whole CPU system. If you go to nearby a DRAM bank, for example, and you have more memory bandwidth, application in class 1A, which is DRAM bandwidth bound application, is just going to benefit even further from the higher internal bandwidth that the DRAM bank, the place the computation nearby the DRAM bank might provide. So I think this is, one good highlight of this work, because these classifications of boundness are independent thing. They're not so tied to the NDP system organization itself. They are tied to the perspective of the host. So now you can, if you just want more bandwidth, just move the computation. Of course, we need to change the application. So closer and closer to the DRAM chip itself, so it can provide more. The DRAM chip can provide more and more and more bandwidth. For example, for a DRAM bandwidth bound application, similar for latency bound applications, right? If your application is latency bound and you want to achieve higher performance when moving the computation to the logic layer, maybe you don't put the application in the logic layer, because then you need to go through the memory controller that is in the logic layer, the TSVs, all of that. But you can move maybe to each layer of the DRAM chip or nearby the DRAM bank, all those type of things. And then your performance is just going to increase even further compared to what I'm showing over here.
Okay, yeah, that makes sense. So your classification is from the perspective of the host system. And the benefits that you get with NDP architecture can become even better if the near data processing becomes even more near to the data itself. Yeah.
Yes.
Okay. I think there are no more questions. I think there's one question on where the paper is, but paper is on archive. You can find it in the link in the YouTube description. I think Geraldo also has that link somewhere in the slides. If not,
it's fuller on.
Yeah. Any other questions?
I would also want to ask you, Geraldo. So regarding the classification that you made, these 6 classes, did you validate? So other than the validation that you showed, these 100 other functions that clearly can be classified in each of these 6 classes as well. So did you try any other way of clustering the workloads, like automated tool or something like that?
Yes, we actually did, and more than one actually. So in the paper, we use another way. Even in the paper, we show a dendrogram clustering of those applications, a hierarchical clustering, which we use the same metrics that we use to do this classification. We put as input of the histogram, the hierarchical clustering algorithm, and then it clustered the applications by itself, and then you see exactly the same 6 classes of clustering. So this is one initial point. And then later on, this is not in the paper, but we did this study because, sorry, this is something that we were quite curious to see, is that if I just throw all of this huge amount of data that we collected and we push it to some classifier and we test a lot of different classifier, decision trees, random forest, SPMVs, all of those different type of classifiers, what is going to happen? And then by doing this clustering, we saw that we could, in the end, end up in the similar 6 classes of data movement bottlenecks that we are seeing over here. However, by doing what we are losing when you do this automatic classification using those, just inputting a bunch of data to those tools, was the insights. We are just getting some clustering, and in the end, we don't know which metrics were used for what, and how they were being an indication of, or why the NDP would benefit or not benefit from the offloading compared to the whole CPU system, for example. So I think this is why we couldn't, from the start, just collect all of the data that we collected over here and push it to some classifier, because we didn't have the insights yet, or that we could obtain by doing this analysis we did over here.
So the insights from your work can be used to train some classification tool, right?
Pretty likely, yes. We're quite confident that it can be done.
Mm-hmm. Okay, thank you.
Okay.
Hi, Geraldo. Thanks for the nice presentation. So some people might be interested into use or build on top of the DAMOV simulator, right? So maybe it would be good to briefly explain what are the current limitations of the simulator, and if these limitations can be overcome, and also maybe possible extensions or future work in the simulator. So basically, for what the people can use your simulator right now, and if there is room for improvement in the simulator.
Yes, yes. So thanks, Luis, for the question. I think I'm going to highlight 2 limitations of the current setup that we have. The first limitation is the fact that we, as I said before, we do not enable concurrent execution of host and CPU, of the host and CPU system. So I'm going to show later when I do the tutorial how to run some simulation. But basically, we have application, and you have 2 simulations, one for the host, another one for the ping, and then you compare the simulation statistics. So ideally, we don't want that. Ideally, you want to run, you want to mark somehow in the application which region I want to offload. Then I want to run some simulation in the host part, reach to the offload point, then do the computation in the host, in the NDP system, and then continue in the host. But right now, this is not enabled in the simulator. So this is one of the current limitations, this concurrent execution. And how to solve this? Basically, we need some coherency model between the host and the NDP system. And there are many, many ways to implement that. But right now, we are not leveraging it. For example, one of these ways from our group itself is from one of our alumni PhDs, Amirali, which he proposed he has 2 works, one called LazyPing, another one called Conda. And those works propose different coherence protocols between host and NDP system that minimize the overheads of maintaining this coherence. So if one would like to do this using the DAMOV sim, would be quite interesting to implement such proposals in the simulator itself. The other problem is would be to enhance the communication or the synchronization or coherence protocol across NDP cores. And for that, again, we have some work in our group from Christina called Synchron, which exactly propose some way of doing smart synchronization primitive for NDP's core itself. Right now, this is not implementing in our simulator, but it could be. If I'm not mistaken, I hope I'm not. Christina actually used some version of the ZSIM simulator to do that. So it's possible to do this implementation using a similar version of our simulator. So I think those are the two most important limitations, I think, or current limitations of the simulator. And I think I gave some examples on how to overcome them. And I'm constantly working on DAMOV sim. Not only me, we are as a group, we are constantly working on the simulator. And pretty likely at some point we are going to release some newer versions with more features that probably are going to overcome some of those limitations.
Okay, thanks for the clarifications.
Thanks, Luis.
Geraldo, maybe you can show the DAMOV sim repo slide so that people can see where it is. I think the link is
it's in the bottom of the page.
Under the YouTube description also. So if people are interested in using the simulator and the benchmark suite, it's completely open source and freely available. So you can download it. There are tutorials. Geraldo is going to talk about a tutorial soon, or give a tutorial soon, but anyone is welcome to download, contribute to it, extend it, and give us feedback related to it as well. I think I'll ask one question related to your application clustering. Now you've analyzed performance and energy for all application classes, which is, I think, nice. It's good to, and one of the important motivations for data-centric architectures is energy consumption, right? Reducing the energy, since a large fraction of the energy is spent on data movement, and data-centric architectures reduce that energy. Your application clustering takes into account only performance metrics. So if you go back to that chart, I think, where you have this tree where you show all the clusters.
Yes.
I think it's good to visualize it. And it's not necessarily needed, but I think it's good to look at it well.
I found it. Yes, it's over. It's this one.
Yeah, this one. Yeah, basically, if you look at this clustering methodology of applications, functions, it's based on performance metrics, right?
Yes.
And in the end, you look at suitability in terms of performance. Well, what about energy? You showed some energy results, and looks like energy is also good. So maybe follows similar trends, but are there metrics to consider for energy optimization?
So I think this is an excellent question. We see this in the paper itself. We see the similar trends from applications from a class based on performance, but later on when you analyze energy, we not necessarily see exactly the same behavior from the applications within a class. I think I briefly talk about this when I talk about compute-bound applications, where I said that even though those applications does not benefit from NDP in terms of performance, we see in the paper that some applications might benefit from NDP in terms of energy. So I do expect some alteration if you repeat this clustering over here in terms of energy also, and maybe ideally we could unify both, right? If you use a metric like, then you can pick your favorite metric, right? What is more important for you? You can use EDP, and then you can square the E or square the P if you are more related to, if your application scenario is more important energy or performance, and then based on that you can create different clusterings for these particular applications. But yeah, so I think would be quite interesting to repeat this clustering based on energy to see basically which applications are going to remain and which applications are going to not remain in the same class. I just want to make another point really quick, that for some applications, we do see the same trends related to energy and related to performance. Mostly those are the applications that, let's say, are the memory bottleneck are more well-behaved, like DRAM benefit bound. Yes, we see the same trend related to energy and related to performance. And DRAM latency bound applications, we also see similar trends related to energy and performance. And if I'm not mistaken, also L1, 2, and L3, and L1, 2, and L2, L1 and L2 cache capacity application, we also see similar trends. For the other ones, it might depend, because then the boundary metrics becomes a little bit more interchangeable. Like, for example, the last first miss ratio or LFMR value, which is an excellent indication of the energy traffic that you're going to have in the system, because this is basically showing if you're filter or not filter in the cache hierarchy. This value goes from low to medium from applications that are in class 2B, for example. And then we see different behavior in terms of energy for application in this class. And then for that would be interesting to either use a metric that use energy and performance at the same time as NDP, or to have a second classification for energy itself.
Okay, that makes sense. And I think that's probably good for future work.
Yes.
To build on the methodology and the workload suite you developed.
Yes.
Okay, are there any other questions?
Yeah, I have one question as well, Geraldo. So I would like to know, like, what is like the difference in bandwidth that you get on the logic die with respect to what you could get through an interposer into like a SOC die?
Okay, so
yeah, go ahead, please.
Okay, so the in paper, if you look at the HMC, for example, specification HMC2, the peak bandwidth that you can get inside these numbers might change because the specification of HMC is a little bit blurry. But yeah, so if you look at the peak performance, the maximum off-chip link bandwidth that you can get is around 120 gigabytes per second to 240 gigabytes per second, depending on how you configure the system. And the internal DRAM bandwidth goes from around 320 gigabytes per second to 420 gigabytes per second. However, this is peak throughput, and this peak throughput is often not achievable, right? So usually you achieve around 80% of that. In the introduction of the paper, we do experiments to see actually the difference in bandwidth for internal and external using a simple stream benchmark suite. And then if, don't quote me on those numbers, but I think the bandwidth that you see from stream, for example, copy used in the whole CPU system is around 70 gigabytes per second. And inside the DRAM device itself, you see something in the bulk part of 400 gigabytes per second. I think a good point to see this difference is I have a plot. I just got reminded I have a plot that actually shows this. That is this one. So yeah, so here the bandwidth saturates around 100 something, maybe around 120. And over here, I mean, almost at 450 gigabytes per second. So
okay. Yeah, but then like if over the time, like integration technology improves and we are able to stack DRAM dies on top of logic dies, and then eventually, like, would you still call near memory processing something where you just stick this kind of 3D memory on top of a traditional SOC die? So, is there any fundamental difference that still needs to be made, or it is just about bypassing the cache hierarchy?
No, I think the fundamental difference. So I don't think, like, I don't know if it's possible because the whole point is data movement, right? This is the whole point of moving stuff closer. So it's not about the bandwidth, but for example, avoiding the number of pings, like, and these pings, like right now in the 2D system, those are like traditional pins in a PCB board, but it can also be micro bumps in a 2.5D type of interconnection. Or it might be, if you move it even further, these pins might be I don't remember exactly the name of the interconnection that you do for TSVs, but might be that that pin that connects the CMOS layer with the TSV and the memory device itself. So I think like this is the most fundamental part, like avoiding this movement from where the data is through where the computation is going to be done through whatever interconnection that you have. So I think the definition just starts to move further, further and further away from the CPU and closer to the DRAM. Just push it to the next off chip link,
I see. So then I can play a game with you then and tell you that I can do more near memory computing by just placing some processing in the bank, right? Instead of going, no, that's also like that would be the next step too.
Instead, I think the end goal would be to do something like the ultimate goal of data processing is to do something as a monolithic integration, right? Like where there is no difference at whatsoever what is computation, what is memory, and like everything is just interconnected in the same chip itself. So otherwise, if you don't reach to this point, I think you're correct. Just move to the next level, or just push it to the next level.
Okay, thanks a lot. That makes sense.
Thank you.
So I want to very quickly ask you something related to the first question from David, and related to this plot that we see here in the NDP side, because it doesn't saturate at 256, right? So apparently, I mean, even though we cannot fit in the available area of the logic layer, theoretically, we could fit more cores. So could you comment on that? And if possible, not only related to this class 1A, but also other classes, whether you have observed that you could even increase more the number of cores. And also one second question related to this is, if you cannot, okay, we obviously know that you cannot fit 256 cores or more, but you could do something else maybe to try to exploit all that bandwidth that is available.
Yeah, this is a really good question. Actually, for we did some experiments in the, it's not in the paper, but we did it internally because we are interested to see if the bandwidth would saturate for the NDP core also, and it does saturate. For example, from a string copy, which is the most bandwidth bound, like one of the most bandwidth bound applications because it's just streaming and copy, we see that it saturates. It reaches the peak actually at the next level, 512, and then it drops at 1K cores. And it starts going down, it does not go down necessarily, but it flats out after that point. So we did the experiments, and then we saw that actually the NDP core design, the NDP system does not provide infinite bandwidth. At some point, it saturates also. And also for the second question, actually I forgot the second question.
So the second question is, if you cannot fit 512 cores, what could you do?
Yes, so if you cannot fit 512 cores, you can play some architectural tricks, for example. Because, for example, we did these experiments at some point that we kept the number of cores fixed, and then we instead of increasing the whole organization of the core, we start increasing the instruction window. And then we saw that by increasing the instruction window itself of the out-of-order core design, and of course the fetching state, all of those type of things, all of those front-end structure, we could start exploiting more and more bandwidth without paying the overheads of the whole area of the out-of-order cores. Of course, increasing the instruction window is not cheap; it's a quite expensive design, but it's something that you can do. It's still cheaper than placing another core over there in the logic layer of the 3D stack device. So maybe you can have 4 cores, but with the instruction window that is the size of the 64 cores, for example, and then you don't pay for the dispatch stage, you don't pay for the cache, L1 cache, you don't pay for the arithmetic units and the floating point units in the execution state, all of those type of things.
Okay, so the point is to achieve more memory level parallelism.
Exactly.
Right?
The goal is to achieve
probably
more parallelism.
You can also use other techniques like exploiting TLP or SIMD or something else.
Yes, exactly. You can exploit TLP, exploit SIMD. You can do fancy stuff like memorizing some routines and replaying them. This is also possible. All of those type of techniques exploit somehow in our area of the other MLP in the system.
Okay, sounds good. Thank you, Geraldo.
I should probably say that the benchmark suite developed in this paper could be useful for exploring such microarchitectural and architectural design spaces of the near data processing systems, right? For example, do you want to do more multi-threading?
Yes.
Do you want, or do you want to trade off between core complexity versus core count versus multi-threading level? It's certainly having an open source workload suite and a classification of the workloads in a methodical way could be useful for understanding how to design the microarchitecture of the near data processing system.
Exactly. Yeah, and the good thing that the DAMOV sim and ZSIM itself is extremely flexible in order to change those parameters. So it's quite easy to do that type of evaluation. And since that seems quite fast by itself, and since the emulator is quite accurate, you can do these evaluations without much effort.
Geraldo, I have another question. So
Sure.
according to you, what is actually making like the distance, no? When we are saying like a memory to computing units distance, is it more the fact that you have to go off chip, or the fact that you have like a deep cache hierarchy that you're not using?
I'm going to be like give a not polite, the diplomatic answer. I think it's both. I think actually it depends, right? For example, I think it's both, but it impacts different data movement bottlenecks in different ways. For example, we think for example, for class 1B applications, those are latency bound, right? We discussed a little bit in the paper that we could improve the performance of the application even in the whole system by bypassing the alternate cache itself and going through the off-chip link and access DRAM. That would already be enough to improve performance. However, that is not enough. Like the NTP system still have some advantages when you go inside the logic layer itself, because of the off-chip. Particular when you consider something like HMC, there is some serializer, some serializer, some deserializer logic. There are some packages being created. All of those things related to access issue a memory request becomes also a source of memory latency. There is also the fact that other than the interconnection network itself, we observe for applications in class 1B that one problem was being that the DRAM, the memory controller queues were saturating too fast when you are doing the application off chip, because pretty much the latency is too high, those queues are too small, you start issuing a lot of requests, and then the latency versus bandwidth curve is you can imagine like a kind of a S curve, where when the bandwidth starts to saturate, the latency starts to, instead of being linear, becomes exponentially. So this is another problem that can happen. So yeah, at summary, I think it's a combination of everything, and it might, the most important thing, if I have to choose one, would depend on the class of data movement bottleneck or of the particular application.
Yeah, thanks.
I have a question, Geraldo. Thank you for nice work and presentation. My question is about the clustering methodology that you have used to make these groups. I think it was previous slide. So anyway, yes, yeah, about that clustering. Yeah, exactly.
Yes.
So my question is that have you seen any application that over the runtime the type of the class may change? I mean that, for example, for a neural network sample, so we have some layers that may go maybe more DRAM bandwidth, let's say class, but there are some layers that can be more compute bound. So how do you classify those kind of applications that during the runtime their states, let's say, may change?
I see. So this is a good question, but over here we are doing the classification per function, right? So even though a function might vary, the behavior of a function might vary across phases of the application, and we actually have some observations based on that. Not in the paper, I guess, but we do some classification based on that when we were doing develop this work. It's more homogeneous within a function. The function is not always usually large enough to change between the classes of data movement bottlenecks. But yeah, so it happened actually. I cannot think about the example from the top of my head. I think it's some application from Splash or from Parsec or something like that. That there is a single application, and this application have more than one function that was identified in step 1, and one function is classified as in one bottleneck class, and another one is classifying another bottleneck class. So probably if you run this function end to end, probably the bottleneck is going to start shifting across the function across the classes. And of course, that application that is known to have behaviors when you are executing the application. For example, different layers in a neural network, in a convolutional neural network, they have different memory characteristics and compute characteristics, and for that we do expect the bottleneck to change across the bottleneck classes. But I think overall you can still use the same methodology to classify the function. The only difference over here is that your classification now needs to be runtime or per phase or something like that, some more dynamic type of classification. But the metrics itself and the methodology itself can still be applied, I guess.
Yeah, exactly. Actually, my question was somehow going toward that point, that how do you guarantee that these 4 metrics that you have here is a perfect matrix? Do we need more metrics or maybe less metrics?
Yeah.
How this is perfect metric?
Yeah, I cannot prove that this is perfect, and I guess we never do this claim. So this is so we try to prove that this is accurate based on the number of workloads that we evaluate, and by doing this evaluation or of this methodology in different ways. So we expect that somehow this classification is reliable. But I cannot prove scientifically that this is the best combination of metrics. I don't even know if this is possible.
Yeah, basically, statistically, you think that these are good metrics, right?
Statistically, I think this is a good metric because you calculate the accuracy and validate this using different methodologies. But to make, I don't think that's possible to.
Yeah.
Extremely hard to make sure to say like those 4 metrics are the best metric to use always for evaluating data movement bottlenecks in a system.
Yeah, I think that makes sense. I have actually a very quick follow-up question. Can we use your methodology or simulator can be used for predicting the behavior of the application somehow?
Yes. So I think we start to do some studies on that. So we cannot, because like we already run 144 function. You classify the data movement bottlenecks and they speed up for those functions in different system configurations, right? And then I can simply take all of these metrics and put it to a system, and based on those metrics predict what's going to be my NDP performance, right? But this is too close to Gagan's work, for example, which is called NAPEL, which he does is not a classification of data movement bottlenecks, but he proposed to use machine learning itself, if I'm not remember, I think is by using random trees and some other machine learning techniques, where he collects some metrics or he runs some simulations from application, he collects some metrics, and based on these metrics, it can tells you the performance of the application in the NDP system. So the same methodology could be applied by using the classification that I provide over here. What is the advantage? The advantage is now that over there, he selected the metrics kind of blindly. There is a list of metrics, and he lets the tool decide which metrics are the ones to define the data move, the relevance of the NDP offloading and the speed up. And over here, we nail down those metrics to 4. And then you can train the same thing, the same machine learning tool with those 4 metrics and the speed up that we observe from those 3 system configurations, and later on predict the performance that we can expect from a particular new application that has not been observed.
Thanks so much. Yeah, that's
Thank
great.
you. So if there is there other question?
Okay, I think if there are no more questions, then we should probably move on to your tutorial.
Yes. So now I'm going to.
I guess
Sorry,
before you start, well, I guess let's wait for some time to see if there are questions.
Okay, great.
Okay, it doesn't look like there's anything, so maybe we should just get started on your tutorial.
Okay. So now I'm going to provide an overview tutorial on both our DAMOV Sim benchmark suite and also the DAMOV benchmark suite and also the DAMOV Sim simulator. So this is the outline for this tutorial. First, I'm going to explain how you can download and install both simulators and the data movement benchmark suite. Also, I'm going to explain how you can compile the workloads, how to install the DAMOV sim, how to generate configuration files to execute simulations, and how to execute a simulation and collect statistics for your further analysis. So first, starting with downloading and installing DAMOV sim. To download and install DAMOV sim is quite simple. You just need to clone our GitHub repository as the first step. And after you do this cloning, you're going to see 4 main files and folders. We have first the one script that's called get workloads, which basically is going to download the set of workloads from another repository and install in your computer. This is required because the benchmark suite can be quite large, because we are evaluating some applications that requires really large input sets, because those are often the more data intensive applications. And then the size of the workload suite itself, including the application, the input set, after downloading is around 9 gigabytes. So it's quite large. So this is why we decide to split the repo using this get workload. So if you only are interested on the simulator, you can just download the repo without having to store 9 gigabytes of workloads that you are not going to use. Then you have license files, README, and then you have the simulator folder itself. So after cloning the DAMOV GitHub repository, you need to download the simulator. Pretty much you execute the get workloads.sh script, and this is going to download the workloads, which is compressed in three different compressed files. Going to extract and delete those downloaded files, and then it's going to create a workload folder that is going to contain all of the benchmark suites that we are using to develop the DAMOV benchmark suite itself. So after you do this, you need to compile the applications, right? And then instead of letting you or the user to compile one application by reading the README of each one of those benchmark suites, which can be caused exhausting, we provide some help in compilation script. But first, we have some notes. The first note is that those workloads or those benchmark suites that makes part of DAMOV comes from other DataMove or other benchmark suites. For example, we have Parsec, or we have Darknet, we have Splash, we have Chai. All of those benchmark suites might have their own set of dependencies. So please make sure that if you cannot compile application by using the sample compile scripts that you provide, to give it a look at the dependencies of the particular benchmark suite in the README of the benchmark suite benchmarks itself that you are interested in compiling. As I said, we provide some helping scripts compile the application, and then those scripts are called compile. So after downloading the workload suite, we are going to the downloading script creates the folders for each one of the benchmarks. And if you go to the folder in the for each benchmark, you're going to see in the first level of the folder a script called compile. And if you run this script, it should compile the application as long as you have the dependencies installed. So here I have an example. I download my workloads, and they are stored in the workload folder automatically by the script. And then I want to compile the stream benchmark. And then I enter the stream benchmark suite folder. I execute the compile script, and then automatically I'm going to have all of the binaries for the stream application. So there is another point that is important to have over here. As I keep saying, the analysis that we did so far are based on functions. So it can be the case that I have a single application with multiple functions that are interesting to offload to NDP, or interesting to see if they are memory bound or not. And the compile.py script are going to automatically generate a single binary per memory bound function. This way you can execute simulations for all of those in parallel. You don't need to serialize and go and back and forth and compile the applications in different functions, for example. Then this is quite simple. And then you have how to install the simulator itself. So to install the simulator, again, we provide some simulators, some scripts to facilitate the compilation of the DAMOV sim itself. So you simply go to the simulator folder, then you run the setup script. This script is pretty much going to install some dependencies that ZSim or emulator have. And this is why you need to run it. This is in sudo. And after that, you just run .script compile.sh, and this is going to compile ZSim, compile emulator, and by the end you should have the message that is over here. The execution should be, the simulator itself should be compiled without much of a problem. To execute the simulation after you compile the simulator, you simply run this command over here, build opt ZSim and a configuration file. Next, I'm going to explain how to generate this configuration file for different configurations, different system configurations in more details. And for that, we also provide configuration scripts and template files for the system configuration that we evaluate in this paper. So how you can generate those configuration files? So the DAMOV sim simulator can simulate many different system configurations. Or I highlight over here the ones that we simulate in the paper. So the first one is the host CPU, which is a host CPU with private L1 and L2 caches and a shared L3 cache. And in this case, the L3 cache itself is of a fixed size. Then we have a host with prefetcher configuration, which is exactly the same as the host CPU, with but we have now a stream prefetcher enabled in the system. And then we have the host NUCA system, which is similar to the host system. So it's a host CPU with private L1 and L2, a shared L3, but now the L3 is organized in a 2D mesh type of network, and the less level cache size is going to increase as a factor of the core count. So, and this is the host NUCA system. And finally, we have the NDP system. Again, it's just an NDP system with a private L1 cache. So we provide several template configuration files under this folder, the simulator template folder. And over here highlights all of those template simulator files that we provide. The user can be free to change those template files to generate configurations. And those template files are for 3 different core organizations. First, in all the core, that's a simple one issue type of core. Then you have the out-of-order core that I keep talking about. It's a simple out-of-order core. And then you have this accelerator model. What is the accelerator model? So when I was explaining the NDP accelerator case study, I was talking about the Aladdin tool, right? What does the Aladdin tool does? It takes the application, and then using LLVM, it generates the data flow graph of the application, and based on the data flow graph of the application, it creates a data flow accelerator target for that particular data flow graph. And then you can create constraint files to say what is the number of function units that you have that can, and then you pretty much is a matching, a graph matching or placement algorithm that needs to be executed, right? Based on the data flow accelerator, data flow graph. Since that sim that we use to develop DAMOV sim is based on PIN, which is also a instrumentation, or is a tool that gives us as a instruction trace of the application during the execution. We replicate this accelerator model in Aladdin. It's not exactly the same, it's more simplifying, because we over here, even though you do the same thing per basic block, we go to the basic block and you create a data flow graph, and then during the execution we can issue all of the structures that can be issued in parallel, respecting the data dependency within the data flow graph at a single cycle. But all of the memory accesses are simulated depending on the memory hierarchy or memory system configuration that you take. So in this case, this is different from Aladdin in the sense that you don't provide a restriction file. So this is an ideal accelerator, ideal in the sense that the compute part of the basic of the data flow graph is going to take the minimum time that it should take, because you are exploiting the maximum ILP inside the data flow itself. However, the memory access latency is going to take the time depending on the different memory system organization that we're evaluating. So then the next step is to create a command file. What is the command file? A command file is pretty much something that's going to define the application, the benchmark suite, the application and the function that you want to execute. Is also going to contain the binary path for the application and also the input set for the particular binary. We provide command files for all of the 144 applications functions that we have in DAMOV to facilitate the execution of the process. So here, for example, I highlight a configuration file, a command file for the stream benchmark suites again. And here you can see that we have in the command file for stream the benchmark suite, which is stream, then the application that I want to execute is adds, then the function inside the application is also called add in this case. And then you have the binary of the application. This binary matches exactly the binary name that was generated with the compile script. And then you have the input for the application. In this case is the number of threads in the system. And this number of threads is in caps lock because this is going to be a parameter for the generation of this configuration file. So after that, the next step is generate the configuration file itself. And again, for that, we provide scripts, and this script is called generate configuration file. This script is going to take both command file and template file that I just explained in order to create simulation configurations for a particular command file. So here again, we are interested on the stream to create a command to a configuration file. I pretty much execute the generate config file script by passing as argument the command file that I'm interested in generating configuration files for. And after that, you're going to see configuration files for many of the system configurations that I just explained. For example, the host using accelerator, the host using other core, the host using out of other core, the pin accelerator, the pin other core, and the pin out of other core. And if you go, for example, inside the host of the core configuration, you're going to see configurations for the system that uses prefetches and configuration for the system that does not use prefetch. And then inside the no prefetcher, for example, folder, we have the benchmark suite, in the case stream, as indicated in the command file. Then we have a bunch of core setups. We have 1 core, 15 cores, 256 cores, 4 cores, and 64 cores. And finally, we have the configuration file for the 4 different applications that the application functions that we analyze for the stream benchmark suite: add, copy, scale, and triad. So now I'm going to briefly talk about what is in the configuration file. So over here, I'm going to highlight some important parts of the configuration file for the add function in stream in 4 cores. The first thing that I highlight over here is that the type flag defines the type of the core that we're going to execute, and this can be out of order core, timing, or accelerator. Timing is referring to the in order cores, is how ZSIM calls the in order core model, and core defines the number of cores that you want to execute, in this case 4. Next, we have the cache organization, and this is a whole CPU system that I'm analyzing. And then you have the hierarchy of the cache. You have the L2, the L1 data cache, the L1 instruction cache, L2 and L3 caches. And then you can define the cache size and the organization. You can change it in the configuration file. And also you have the memory controller device that is going to be used, and the memory device itself that is going to be used in the simulation. In this case, we use Remulator as the memory controller, and we use for this particular configuration file, HMC as the main memory device. It's important to say that Remulator itself enables a very number of memory devices to be simulated. HMC is example, but you can change it to HBM. You can change it to DDR4, DDR3, low power DDR, all of those type of memory configurations. All of those configuration files are available under Remulator configs folder. And finally, we have some simulation parameters that are important to control the simulation. For example, we have a highlight over here, the pin mode flag. This pin mode flag is going to enable or disable the execution of pin in the system. So if you put a false, it's going to be whole simulation. If you put true, is a pin execution. and you have the maximum number of loading or total instructions that are going to be executed. This is going to control until which point the simulation is going to be executed, and after that point is reached, the simulation is going to be terminated. And finally, you have the command file for the application that's going to be simulated, and this is automatically generated using the script, the generate config file script that I just explained about. So after you do all of this, you can finally execute a simulation. So to execute a simulation after, if everything works properly, and it should, you can just, for example, run the stream add application in a whole CPU system with 4 cores. To do that, you just pass the binary of ZSIM and the configuration for the particular application that you want to execute. And then again, if you want to do the same simulation in the NDP system in the 4 cores, you do the same, but now you pass the configuration file for the pin core with using out of all the cores and 4 core counts for the add application. As I think I mentioned before, it's important to highlight again that the DAMOV sim does not support concurrent execution on host and NDP core. This is why you have to do step 6 and step 7 separately, and after that collect the metrics. And how you can collect the metrics? After the simulation is done, the statistics are going to be saved under zsim/stats folder. And if you look at the folder for the host and the pin cores, we are going to have 4 main files. The ones that I highlight here that are important ones are the files that ends on .formulator.stats. This is going to store all of the simulation and statistics regarding to the memory simulation. So you're going over there. We have Dram row conflict, for example, Dram bank row hits. You have Dram row misses. You have Dram average Dram access cycle, the Dram band. All of these statistics are over there. And you also have the statistics regarding to the CPU execution over under the file ended in .zsim.alt. And then over there you can see files like statistics regarding, for example, the cycles that took to execute this application, the number of instructions that was executed, the breakdown of instruction types, all of those type of things. To facilitate collecting the data or the statistics of the execution of application, we create another script that is called get stats per app application. To run this script, you just pass the script. You just run the script with one of the zsim.out files over here as an argument, and this is going to generate a summary of the execution of the application. It's going to provide metrics that provide a quick understanding of the characterization of the application. So it's going to provide the number of instructions that was executed, the number of cycles that it took, the IPC of the application, the L3, L2, and L1 miss ratio, the L3 MPKI, and the last first miss ratio value. And if you do this, and you can do the same for the pin system, it also provides the other metrics I just cut over here to fit on the slide. And based on that, for example, if you are interested or compare the performance of the host and the NDP system, you can just divide the one PC by the other. And then in this case, you can see that the NDP system provides 1.6 times performance benefits. But you can also see other metrics like the last first miss ratio or MPKI of the host CPU system, which can be interactive metrics. So I think this is pretty much a tutorial of how to use DAMOV and DAMOV sim. If you have any questions, feel free to post on our GitHub or to email one of us, of the authors of the paper, myself directly, and I'll be glad to take the questions. So thank you so much.
Okay, thanks, Geraldo. Maybe you can also show the GitHub and the link again.
Okay.
It's in one of those slides, but
yes, let me go back
so that people can take note.
Sorry.
And maybe people can prepare questions in the meantime if there are any more.
They're almost there. This slide over here. Okay, this one.
Okay. Okay, I guess, are there any further questions? Juan, do you have any other questions or comments?
Yeah, just a very quick question about the simulator. But I mean, how extensible it is, because you showed your experiments with NDP configurations, or what we also call processing near memory, right? What about other types of processing near memory? So you're placing the cores in the logic layer. How about extending the simulator to support something like near bank computing, similar to the AppMem or FIMDRAM, or even further, computing inside the memory, like processing using memory approaches?
Yeah, it's a really good question. ZSIM and the good thing about ZSIM and Ramulator is that both of them works on C++. So if you are familiar with C++, it's quite easy to extend to do this type of things. So if you want to, for example, to do near bank processing type of computation, it's just a matter of changing the memory controller device inside Ramulator to exit to forward all of the memory requests directly to that area of the DRAM chip itself. So it's pretty much playing with pointers and point to the correct place. Of course, I'm simplifying the whole thing over here, but it turns down to that. So it's not that hard. For the processing using DRAM or processing using memory itself, it can be a little bit more complicated, because now you need to create new DRAM operations inside the Ramulator itself. But it's not as hard, because pretty much you just need to create a new instruction for that. You can use the same methodology that you use to demarcate the area that you want to offload, to create a new instruction that is going to execute this operation. And later on, you can just modify the DRAM controller inside the Ramulator itself to issue, for example, let's say if you want to do something similar to Ambit or SimDram, which executes book bitwise operation using triple row activations, you can just create these new comments on the DRAM comment class, DRAM controller class of a particular memory device in Ramulator itself. So in the sense, as long as you're somehow familiar with C++, I think it's quite easy extensible, those simulators.
Okay, and what do you think about an extension of or analysis of the workloads, the DAMOV benchmarks for these different types of? So could them be useful for different types of processing in memory, or near data processing, or processing using memory, and so on?
I think they could, and be quite interesting to do as a follow-up work. For processing near memory, it's easier, because it's easier to write code. For example, if you do this extension that I just mentioned for processing near bank, it would be quite easy to repeat the same experiment and evaluate the applications, because we don't need to change the applications. But if you want to do something similar to processing using DRAM or processing using memory, it can be more time-consuming and it can be harder, because for that, you need to rewrite the application, right? So, for example, if you want to do book bitwise operation, you need to go to application itself and you write the book bitwise code using the correct set of operations to do the computation. And then after that, of course, you can use the simulator and redo the analysis. But there is this non-trivial first step that needs to be executed before doing that.
So for now, you need the user to be able to identify those parts, right?
Exactly,
so
exactly.
Hopefully the benchmarks can also be used to develop some sort of tool or methodology that can help as well in identifying those parts.
Yeah.
That
so.
suitability. Mm-hmm. Okay, sounds good.
Thanks, Juan.
Thank you.
Yeah, I think there's one question from YouTube which says, can we modify the accelerator architecture by maybe using some other tool than Aladdin?
So just to clarify, we are not using Aladdin to do the accelerator in the DAMOV sim anymore. We do the same, we follow the same methodology that Aladdin does, and do the accelerator itself, to do a data flow graph accelerator. I guess you could, and there are other tools that to develop accelerator design for a particular application. And I guess you could use those tools to generate automatically accelerator, because as long as the tool has some capability or portability with C++, you can just migrate the code over there, and then it's fine. And of course, you can also create you could create a new core model inside ZSIM if you want to create a completely custom accelerator, and then to create this accelerator inside ZSIM and with a new core model and execute some new simulations. This is totally possible to do. And this is what is done, for example, if you want to use Gen 5, for example, you follow a similar methodology.
Okay, sounds good. Are there any other questions? Yeah, I don't see anything on YouTube. I guess if there's nothing and if there are no more questions on Zoom as well, then we can probably conclude. It's already been close to 3 hours. Thanks, Geraldo, for the comprehensive overview of the work and the tutorial of the open source artifacts that come along with the work. And just to remind people, they can find the paper on archive, and it's linked in these slides as well.
Yes.
And they can find the open source artifacts on our GitHub repository as the Safari Research Group.
Yes.
Okay, I think we're done then.
Thanks, Honor.
Thanks,
Thanks everyone for the questions.
Okay, take care.
Thank you.
Thank you,
Bye-bye.
Geraldo.
Thank you.
Thank you, Geraldo.
Thank you, Geraldo.
Thank you very
Thanks,
much.
Geraldo. Thank you, Geraldo.